Hello, welcome to Noise Control and its Management. Today is the second last day of this week, which is the 12th and the final week of this course. And what we are going to do today and tomorrow is basically a continuation of our discussions on resonators and how these resonators can be used to reduce noise in specific frequency bands. So, what we have been discussing till so far are side branch mufflers, and we have discussed two specific varieties of side branch mufflers. In the first variation, we had a Helmholtz resonator attached to the side of a tube which is conducting noise, and in the second case we attached a long closed tube to on the side of a pipe through which sound is getting transmitted. What we are going to do today is a third flavor of this kind of resonator, and here we will use an open tube, and this open tube has to be short. So, if I attach, so this is how the scheme looks like. So, this is my long tube, and if this is the cross sectional area and let us say the cross sectional area is S, then what I can do is that I can attach an open tube on the side of it, and this open tube, which is not too long, actually it is short tube, this can also act as a resonator and it can kill a lot of noise associated with a particular frequency. So, if the diameter of this tube is 2a and the length of this tube is L, then I am going to again directly write the results. The amount of power transmitted, it can be expressed as AT. So, in that case 1 over AT is equal to, and this is a complicated expression. So, this equals pi times F L C, where L C is the effective length of this tube, and we have now learned how to calculate it, divided by C times A over L C whole square plus R S divided by 2 pi rho naught C plus C over F L C plus A square over 4 S times C over F L C, and this entire thing is enclosed in a parenthesis, and the whole thing is squared plus 1, and then I divide this entire expression by pi F L C over C times A over L C whole square plus R S over 2 pi rho naught C. Okay, so, this is not a positive sign, rather it is a multiplication multiplied by C over F L C, and this entire thing is squared plus 1. So, through this complicated expression we can calculate 1 over AT, which is the transmission coefficient of this entire device, and the transmission loss is nothing but 10 log of 10 of 1 over AT. Now, if frequencies are small, so and when I say small, I say it in a particular context. So, we will explain that for low frequencies, that is when frequency is small compared to 0.1 C divided by square root of area. So, this is the cross sectional area of the pipe. So, if that is the condition, then I can make some approximations in the numerator and denominator, and the expression becomes much more simple, and in that case 1 over AT equals RS divided by 2 pi rho naught C plus A square by 4S divided by F L C by C, and this entire thing is squared. So, this is a simplified version, and for high frequencies and what do I mean by high frequencies? That is when F is very large compared to C divided by square root of S. In that case, I can write it as 1 over AT actually is approximately equal to 1. So, there is no transmission loss of the energy at high frequencies, and at very low frequencies we can calculate my transmission loss using this relation, and for intermediate frequencies or for the entire frequency bandwidth we can calculate transmission loss by calculating the parameter 1 over AT by this long complicated expression. So, this closes our discussion on the open tube. The next thing we are going to do today and also tomorrow is expansion chamber mufflers. So, here we will discuss a different category of mufflers, and they are known as expansion chamber mufflers or silencers. So, mufflers and silencers, they mean the same thing. So, these expansion chamber mufflers could have one expansion chamber or two expansion chambers. So, this is an expansion chamber muffler with one chamber. Okay. Now, here the area is S1, the outgoing area is S3, sound is coming in from the S1 side, it is going from the S3 side, and the cross sectional area in the intermediate portion is S2, and this length of the intermediate portion or the expansion chamber is L. So, this is what I imply by expansion chamber. This is what the expansion chamber is. So, this is a single chamber design, and if I want to look at multiple chambers or maybe dual chamber, then it could be something like this. Okay. So, this is a dual chamber design. This is a dual chamber design. So, what we are going to discuss specifically is the single chamber design, and in a lot of automotives this is the type of muffler. In a lot of cars and trucks, this is the type of muffler which is used, of course in modified way, but the basic design looks something like this. So, here the sound energy is going in and sound energy is coming from the side S3, and once again what we are interested in finding out is the transmission coefficient, which is equal to W out divided by W in. So, this is my power in and this is my power out, and once I can compute AT, then the transmission loss for this expansion chamber muffler is nothing but 10 log 10 of 1 over AT. Okay. So, let us look at this design once again. So, the single chamber design what does it have? It has an inlet port, it has an expansion chamber, and it has an outlet port. Let us say the cross sectional area at the inlet port is S1, the cross sectional area at the exit is S3, and the cross sectional area of the intermediate or the chamber is S2, and the chamber length is L meters. So, what we are interested in is figuring out what is this ratio W in with respect to W out. Now, you can solve this problem based on whatever principles we discussed in the first part of this course, where we had discussed transmission line equations, because this is a one dimensional flow problem, sound propagation problem, and using those transmission lines we can write transmission lines for first portion, second portion and the third portion, and then we use appropriate boundary conditions at the interface of these three portions, and then we can find out the overall transmission coefficient. So, what I will do is I will not go through that all detailed mathematics which can run into couple of classes, but rather I will produce the results directly. So, we define two parameters. The first parameter is S3 over S1. So, this is the ratio of cross sectional area of outlet port and inlet port, and that ratio is V, and then the ratio of S2 and S1 we define as M. So, in terms of these, the parameter 1 over AT, it can be expressed as 1 plus V square plus M minus V by M whole square minus 1 minus V whole square, and this entire thing is multiplied by sine square k L divided by 4V, where once again k is the wave number which is equal to 2 pi over lambda. In a lot of single chamber expansion mufflers, the ratio of S3 and S2 is 1. So, in that specific case, that is, if S3 equals S1, if S3 equals S1, then M equals V, and in that case we have a much more simpler expression. So, 1 over transmission coefficient equals 1 plus 1 by 4 into M minus 1 by M whole square sine square k L. This is the expression. So, this is the situation when M equals V, and if M is not equal to V, then we can use this relation. So, this inverse of transmission coefficient is maximum when this sine square k L term equals 1. So, we can state that 1 over AT, excuse me, is max when sine square of k L equals 1, or we can say that k L equals n minus half times pi, where n could be any integer, it could be a positive or a negative integer. So, we know that k is equal to the wave number. So, if I express k in terms of frequency and speed of sound, then I can say that 2 pi f naught over c times L. So, this entire thing is the wave number. Okay. So, this equals n minus half times pi, or we can say that the frequency corresponding to which this sine square k L is going to be 1 or it is going to be maximized will be equal to n minus half times c over 2 L. Okay. So, now this is the relation. So, now what we are going to do is we are going to show you how this transmission coefficient changes as I change the parameter L, or actually the normalized parameter K L. Okay. And if I plot my transmission loss, so we know that, so if I plot the parameter 1 over AT, and on the x axis let us say I am plotting k times L, and on the y axis I plot 1 over AT, then I get a curve something like this. Something like this. Okay. So, I'll draw it again. Something like this. Okay. So, so here my KL is equal to 0, KL equals pi radians, KL equals 2 pi radians, and so on and so forth. So, whenever sine of KL is 0, my 1 over AT terms becomes, as per this relation, it becomes 1. Okay. So, 1 over 2, so this axis starts from 1 and it has a maximum. Okay. So, when sine KL is 0, then 1 over AT is 1 and transmission loss is 0, transmission loss is 0 decibels. So, that is what the thing is, and let us say that this m corresponds to some value, let us say it is 40. So, what happens if I reduce m, and what is m? M is the ratio of S3 and S1 or S2 and S1, in this case M and V are same. So, if I change m, then the nature of the graph remains same, but if I increase, or actually if I reduce m, then that is how it looks like. So, this is let us say m equals 30. Okay. So, now that we have developed this graph, I would like to reiterate what I mentioned earlier, that the frequency at which this 1 over AT term gets maximized corresponds to f naught, and that is equal to n minus half times C over 2 L. Okay. So, that is one conclusion we make from this particular graph. The other conclusion we make from this graph is that as m increases, we see that 1 over AT also increases, and if 1 over AT increases, then our transmission loss also increases, and if m the parameter m goes down, then 1 over AT also becomes less. So, this is another thing I wanted to say. So, next what we are going to do is we are going to do an example, and I am going to now define that particular example as it relates to this particular type of silencer, so that we have a better understanding. So, here is the problem. So, based on what we have learned till just now, what we are going to do is we are going to design a single chamber expansion muffler. Okay. So, the problem is defined like this. So, we are going to design a single expansion chamber muffler such that M equals V. Okay. So, this is given. So, which means that S1 equals S3. So, this cross sectional area is S1, this cross sectional area is S3, and this cross sectional area is S2, and the length of this chamber is L meters. And the next thing we are going to say is that D1 is 0.25 meters, 0.25 meters, and the speed of sound in this tube is going to be 337.3 meters per second. Air density is 1.292 kg per cubic meters, and the so we need, so here's the requirement, we need a TL transmission loss of 6 decibels minimum between 177 hertz and 354 hertz. Okay. So, between 177 and 354 hertz we want a minimum transmission loss of 6 decibels. So, this diameter is this parameter D1, which is same as 2A, and so this is the requirement. So, find S2 and L for the muffler. And L should be minimum. So, this is what the requirement is. So, this is the problem. We know that we know the cross sectional area of S1, cross sectional area S3, because M is equal to V, and S2 we do not know, we also do not know the length of this chamber, and the requirement is that we need a minimum thing of 6 decibels between 177 and 354 hertz. So, with these data we have to figure out the value of S2 and L. So, this is what I have set up the problem as, and tomorrow we will actually go to actually solve this problem, and till then have a great day, and I look forward to seeing you tomorrow. Thank you. Bye.